Hi, in this last video of the semester, we'll be talking about the oxidation of alcohols. So there's lots and lots of ways to oxidize alcohols, but we're only going to be talking about a few today. One of the things I'll point out is that we actually have the ability to oxidize alcohols in our liver. So when we ingest ethanol, it ends up getting oxidized to acetaldehyde, which then further gets oxidized to acetic acid. So this is the same acid that's found in vinegar. And this is an oxidation process that happens with an enzyme called alcohol dehydrogenase. So again, remember that oxidation is effectively like the loss of hydrogen gas from a molecule. Let's look at how that occurs for these types of molecules. So there are a couple oxidants we have at our disposal in this class. There is a gentle oxidant, which will take an alcohol to an aldehyde. That is called PCC. So that's the reagent that you would write down, PCC. And we'll look at what that is in a moment. It's important to also recognize that it will take a secondary alcohol to a ketone. So a primary alcohol will become an aldehyde, and a secondary alcohol will become a ketone. Now, a more aggressive oxidant is chromium trioxide in the presence of sulfuric acid. So when this encounters a primary alcohol, it doesn't stop at the aldehyde oxidation state. It oxidizes all the way to the carboxylic acid. But when it encounters a secondary alcohol, it simply stops at the ketone because there are no more carbon-hydrogen bonds that are adjacent to this, adjacent to the oxygen that can be removed. So let's look at the mechanisms of how this works. So first, let's look at a very general mechanism. So this is a mechanism that occurs for most oxidants for alcohols. So you have oxygen, or the alcohol oxygen as a nucleophile, and somehow you have a molecule that will eventually become a leaving group that has some form of a positive charge, or it could have a leaving group built onto it. So you form a bond between this oxygen and this leaving group, and at this stage, a base will come along, and it doesn't have to be very basic typically. It can be even neutral water can act as a base. And this now gives you this oxygen with a leaving group bound, and you have hydrogen atoms adjacent to this. A base can come along and abstract one of these hydrogen atoms to now eliminate this leaving group, so now Lg minus, and this mechanism is very similar to what you've seen before as an E2 mechanism, but this is the oxidation of an alcohol. So let's look at how this occurs with chromium. So PCC stands for pyridinium, so it's protonated pyridine. Chloro, that's what the first C stands for, chromate. So it's a chromium oxidation reagent. And chromium is a relatively toxic and dangerous metal to work with. So again, there are lots of other oxidants that we can use if we want to avoid it. And this particular chromium is a chromium 6 species. So the mechanism involves, again, the oxygen reacting with this thing that will become a leaving group, and you form an oxygen to, in this case, chromium bond. Now, there is a proton transfer step, which effectively involves the proton getting abstracted by water or whatever is in solution, the base that's in solution, at the same time as this negatively charged oxygen is abstracting a proton from something else in the solution. So we call this a proton transfer step. Well, what I'll simply draw as a base and the conjugate acid of that base, both doing their work. So now you have this oxygen-chromium bond, and the oxygen no longer has the formal positive charge. This oxygen can kick off the chloride as a good leaving group, and now you're left with a situation that looks very similar to what I showed you on the previous slide, where this is now your leaving group. And sure enough, the base comes along and abstracts this hydrogen in an E2 fashion to give you your aldehyde, and you're now left with a chromium 4 species. And that's going to be a byproduct that you're going to have to wash away and to deal with in a responsible manner from a chemical waste perspective. Now let's look at what happens when we're able to oxidize past the aldehyde state, so the aggressive one. So with the aggressive one, again, we can now oxidize somehow from an aldehyde all the way to a carboxylic acid. I want to point out that this aldehyde could have started as an alcohol, and again, you wouldn't be able to stop it midway. It would oxidize all the way to the carboxylic acid. So the thing that's important to recognize about this particular, about an aldehyde, is that an aldehyde, in the presence of water, these reactions are done in the presence of water, have an equilibrium with what's called a hydrate. So a hydrate is simply an aldehyde that has an equivalent of water added to it. In this case, I've highlighted the oxygen of the water as being blue. So now that you have a hydrate, you have something that looks a lot like an alcohol, and you can see that you have this hydrogen atom that's been there all along. So now through the steps similar to what we saw on the previous page, you end up forming an oxygen to chromium bond. That whole chromium species is a good leaving group, and you have water now which can act as a base. And again, this proton was here from the very beginning on this aldehyde, and now this hydrate, and now this hydrate that's been activated with a leaving group. The water will abstract that hydrogen atom, and it will go on to form a double bond. Meanwhile, it will kick off this chromium species as a chromium-4 leaving group and give you a carboxylic acid at the end of this mechanism. So again, you'll talk about this interconversion of an aldehyde or of carbonyls to their hydrates next semester, but it's important to recognize that this can occur, and this is why an aldehyde can get further oxidized using chromium to a carboxylic acid. Thank you for your time, thank you for a great semester, and I look forward to questions that you have in class.